In this video, we're going to see that if we know that a function f has a local maximum at a certain point, then we can gather lots of useful information about the derivative of the function at that point. But before we state the theorem that will explain what I'm talking about, it's important to know the definition. So what do I mean when I say local maximum? Well, we have a function f, define an open interval I, and we have c9. F has a maximum at c even only if f of c is greater than or equal to f of x for all x in I. Makes sense. It's the biggest of all values. And then we say that f has a local maximum at c even only if there exists a delta such that if the distance between x and c is less than delta, then f of x is greater than or equal to x. So that means that if we zoom in and we focus only on small portion of our picture, it is the biggest of all the values around it. Maybe farther down the line there is another value that will make things bigger, but the important thing is a local thing, is that very close to c, my function is the tallest at point c. So f of c is the biggest value around. So I will leave as an exercise for you to write a definition of minimum and local minimum of a function. I'm pretty sure you can do it because it's very similar to what we've done before. Now, if we look at this picture here, we have a graph and we can see clearly where there's a maximum, where there's a minimum, and I drew the tangent lines to the graph. And something very interesting that we can see here is that those tangent lines are horizontal. And that is actually quite nice, because if that tangent line actually exists, it's always going to be horizontal. And that's what this I'm going to call local maximum theorem tells us, is that if I have a function that is defined in an open interval, and I know that function f has a local maximum at c, and c is an interior point, this is just to be able to talk about derivatives, then f prime of c is equal to 0 or it doesn't exist. It is impossible to have a function that is differentiable at a maximum point that has derivative different from 0. So this is very nice, because you see, the way we use this is we look at it, and if I know that there's a maximum at c, then I know immediately that either I'm differentiable and the derivative is 0, or I'm not differentiable. And a way we use this in practice, you will see in the feature, is that we look at the values where the function has derivative 0 or that the derivative doesn't exist. That's what we call critical points. And then those are going to be my candidates to be maxima and minima. It doesn't mean that they are, but they are candidates, because we know that if the derivative is anything different from 0, so if I know that the derivative exists and it's a number that is not 0, then I know that there is no hope for my function to have a maximum there. So we're going to get our hands dirty and we're going to do the proof of the fact that if my function has a maximum at c, then f prime of c is equal to 0 or it doesn't exist. And as an exercise, I want you to state a similar theorem but for local minimum. Just try to follow the same ideas and you will see it. So how can we write down the proof? Well, we're going to assume that we have a local maximum at c. We want to show that f prime of c is equal to 0 or that f prime does not exist. So we will assume that f prime exists and we will prove that it must be 0. And the other option was that it doesn't exist. So here what we're doing is that if it exists, then it is 0. Now, since we have a local maximum at c, by definition, f of c is greater than or equal to f of x for all x in some interval centered at c. I call it c minus p, c plus p. Okay? This implies that if h is positive and small enough such that c plus h is still in that interval, then f of c is going to be greater than or equal to f of c plus h. But then that means that f of c plus h minus f of c is less than or equal to 0, and h was greater than 0. So the quotient f of c plus h minus f of c over h is less than or equal to 0 when h is positive. Okay? So we can take the limit as x approaches 0 from the right through positive values of this quotient, and we know that then it has to be less than or equal to 0. Now, what happens if h is negative? So if h is negative and is small enough, then we will have that f of c plus h minus f of c is again less than or equal to 0 because f of c was a local maximum. But now when we look at this quotient, we have a negative denominator. So now we have that f of c plus h minus f of c over h is now greater than or equal to 0. So when I take the limit as x approaches 0 from the left, my limit has to be greater than or equal to 0. But here remember that I assumed that my function was differentiable at c, which means that the left-hand side limit and the right-hand side limit, they both have to be equal. So we have something that is less than or equal to 0 and something that is greater than or equal to 0. Those two things are equal. So the only way that this can happen is if that limit is 0. And that proves that if my function is differentiable at c, then the derivative has to be 0. Now, the converse of this theorem is false. For example, if we look at the function f of x equals x cubed, the derivative is 3x squared. So f prime of 0 is equal to 0. But f has no maximum or minimum actually at 0. And if you don't believe me, I invite you to draw the graph and you will immediately see that at 0 we have no maximum, no minimum. So this is telling me that if my function has a maximum, then the derivative is 0 or it doesn't exist. But if I know that the derivative is 0, I cannot say that I have a maximum.